I'd like to do a survey of some of the Mathematica programs that I've written involving relativity. This one's called Moving Circle Spacetime Cone Cylinder Intersections. And mainly it's the premise is to find the intersection of a cylinder and a cone. Well, I didn't actually necessarily find the formula for the intersection of the simple to remember formula for the intersection of a cone and a cylinder. I did manage to kind of get an animation of it, and this is kind of what it looks like as the cone goes by, or as a cylinder goes by the cone. And the reason I did this was I was trying to find the locus of observed events at a certain time, and what I did was essentially the light cone represents the locus of points currently being observed at the point, at the 0, 0 point. And so in other words, since you have a delay equal or essentially proportional to the distance, the delay time is essentially this two-dimensional, or it's this three-dimensional surface, a surface that just is represented by a cone. Meanwhile, this is a Lorentz contracted object going by, the locus of points occupied in space-time by an object going by in space. And what you find is that as the object goes by, it starts out looking like an extended oval, and then as it passes by, it turns into a contracted oval. Only at the point where the circle is perfectly aligned with your eye, with your viewpoint, only at that point do you see what the standard Lorentz contraction. But when it's coming toward you or away from you, you get a little bit, you get more elongation or a little bit more contraction as it's moving away from you. Now let's look up into the program a little bit. So see if I can remember what some of these variables represent. I remember, for instance, that phi was representing the rapidity. So phi is the rapidity. And the rapidity of an object is related to its velocity. Actually, it's the hyperbolic arctangent of the velocity. So I want to try to describe this relationship between kind of a hyperbolic, a normal, what do you call this? Basically a trigonometry angle and a hyperbolic angle. And what I'm going to do is I'm going to call this y and this x, and then I will say, and as long as if x comma y is on the circle, then tangent of theta is equal to y over x. Now I'm going to do kind of a similar thing with x and a t. And x, if I have an object moving with a certain velocity v, then x would be, this would be the line x equals vt. But say we've got a parabola over here, or now this is a hyperbola, sorry, and the hyperbola is described by let's see, it looks like t is greater than x, so we'll say t squared minus x squared equals 1. And we labeled this angle phi, or phi or phi, or pho or phum. Anyway, if this angle is phi, then we can say hyperbolic tangent of phi is equal to essentially x over t, or which is generally v over c. I may have maybe this needs to be a ct and this be a vt there, to get the proportion proper. I know there's a c, basically it's x. We can just cross that out. X and ct is the way you want to write. You want to kind of arrange it, so ct squared minus x squared equals 1. And maybe put a c down here too. Yeah, that would probably fix it up to be appropriate. There's a further relationship just to kind of like make this analogy a little bit more complete. This area here is a kind of a pie, part of like a chunk out of a pie, and the area of that pie chunk is going to be well, it's going to be pi if you have the whole circle. Pi, let's say pi theta over, is it pi times theta? Pi times theta over 2. So if you go all the way around the circle, which is 2 pi radians, the area is just pi. If you go halfway around the circle, which is pi, I think I still have this, I still got an error. Okay, thinking about it a little bit more, theta, if you just go halfway around the circle, hold on, let me label the angle, let me draw a picture. I'm getting confused. Okay, if you go from here to here, 0 to pi over 2, that area equals pi. If you go halfway around to from 0 to pi, that area is, wait, this area is pi over 2. This area is pi. No, that area is pi over 4. And this area is pi over 2. Okay, and then, so basically you take the angle theta and divide by 2. So the area equals the angle divided by 2. Now, let's do this. This is the relationship that holds up with the hyperbolic tangents, because if I happen to have an angle like this one with angle phi, then the region inside there is area equals phi over 2. And if I have, say, example like this, where it goes way out and comes straight down like that, and you get this area. Now this area, because you can keep extending this line forever, that has no upper limit on the parabola. So the area of that little segment in there is going to be phi over 2, regardless of how you go. And phi has a domain. Phi has a domain. It's a member of the set 0 to infinity. So it can go as high as you want. Over here with the with this angle, theta is a member of the set 0 to 2 pi. It doesn't go any higher than 2 pi because Once you get up to 2 pi, you filled in the entire circle, and the area of the circle is pi. Anyway, so that area being phi over 2 describes what's called the rapidity, or well, phi is called the rapidity of the related to the velocity, and that rapidity basically goes to infinity as the actual velocity, which is the slope of this line. The velocity never gets more than a 45-degree angle, and so the velocity, which is usually given the relativistic velocity, which is the velocity as a proportion of c, always stays less than 1, and so v is less than, I should say, it's always less than 1. It's not less than or equal to 1, or less than or equal, sorry. Velocity is less than c. So you can't have a velocity greater than c, but you can have an infinite rapidity. Okay, this video is exceeding 10 minutes now, so this is to be continued.